Hello and welcome. In this video, we'll talk about the characteristics of polynomial functions. This lesson has been prepared for students who are taking the MHF4U or the Grade 12 Advanced Functions course. Before I start, I must mention that this is probably one of the more essential lessons in the unit of polynomial functions. And I must also confess that I've improved this lesson year after year because it comprises the many tools that are needed to understand the nature of polynomial functions, and I try to organize it to the best I can. So I hope you find the instructions easy to follow and understand. So we're going to get started with the first method of graphing a polynomial function, a method you are familiar with, and that is by using the equation that describes the transformations of any function. Y equals a f k x minus d plus c. And I hope you remember the meaning of each coefficient. A indicates the vertical expansion or compression. K is for horizontal expansion or compression. D is the horizontal translation. And C is the vertical translation. I must add, though, that this method is limiting, and that's why we will discover together or investigate together other methods of graphing polynomial functions. So let's get started. The parents of polynomial functions can be in the form f of x equals x to the power of n. And we can transform any function given in the form x to the power of n by giving them a coefficient a, k, d, or c. When that's the case, then we treat these functions just like parent functions. Example, x to the power of 1 would be the linear, x to the power of 2 the quadratic, power of 3 the cubic, power of 4 a parabola that is narrower than the basic parabola, y equals x squared, and so on and so forth. So I'm taking two examples, or we're taking two examples here together. The first one, f of x equals negative x minus 3 cubed plus 4. The first thing you want to look at is the degree of the function, because that will tell us what the shape of the graph will be like. So this is degree 3, which makes it an odd degree function. The next thing you want to look at is the leading coefficient. You want to know what the leading coefficient is because along with the degree of the function, it will help us describe the end behavior or determine the end behavior of the function. Now, you find the leading coefficient right before x. Now, x to the power of 3 is going to be the highest degree term, and the only coefficient that it will have is the number before the brackets. The leading coefficient, in other words, here is negative 1. So it's a negative number. Now that will tell us that the behavior of this function will start, or the end behaviors of this function will extend from quadrant 2 to quadrant 4, because it's an odd degree with a negative leading coefficient, so it will behave like a linear function with a negative slope. I'll write a note in here. Behaves like a linear or a first degree function, right? Function with a negative slope. So we know the end behavior. The next thing we want to know, or we want to do, is pay attention to the degree, which will determine the shape of the graph. And a third degree function, we know that has an S shape. Now, it could go based on the sign of the leading coefficient. It could go this way or this way around. The next thing we want to look at is the numbers 3 and 4 that we see in this equation. So number 3 will indicate the coefficient d, or determines or helps us determine coefficient d, which is positive 3. Remember that the negative sign, right, has nothing to do with the value of d, so it's negative or minus a positive 3. So the horizontal translation would be 3 to the right. And the vertical translation is indicated by the coefficient 4, so the number 4 we see at the end of the equation. And we'll say that c equals 4, that will guarantee us a vertical translation of 4 up. So if we were to graph x to the power of 3, which I will here with a broken line here, it will look like this. Now, since the leading coefficient is negative, then the graph will start from quadrant 2 and end in quadrant 4. And because we have a translation 3 to the right and 4 up, which will practically be 1, 2, 3, 1, 2, 3, 4, so somewhere in here, then this point here, which is the x and the y intercept of this function, will move also 3 to the right and 4 up, and that will make the graph appear a little higher here. Okay, so this will be the graph of f of x. The next example, we have to graph g of x equals 2x to the power 4 minus 1. So we can do this a little bit faster now because we know what we're looking for. So the degree of this function is 4. So that means even. Which means that this function will behave, or the graph of this function will behave similar to parabola, which is the simplest even degree function. The leading coefficient, a, is 2, so we're going to see a vertical expansion. And we don't see any horizontal translations because we do not see any numbers added or subtracted to x inside the brackets. So horizontal translation, none. And there is a vertical translation, which is determined by this number here at the end, -1, which tells us that the graph has moved 1 down. So if we were to draw the graph of x to the power of 4, it would be very similar to the parabola, but flatter at the bottom and closer to the y-axis, right? The arms. Now, since the graph has a coefficient, or the equation has a coefficient of 2, then this will appear, so this graph will appear slimmer and moved 1 unit down, which will make this graph look more like this. So this would be, so the thicker line will indicate the graph, or will describe the graph of this, will be the graph of this function. Sorry, I got distracted by my pen has low battery. So there is a note in here that I added in, and I kind of mentioned at the beginning of the lesson. Remember that this method of graphing is limiting due to the fact that it can only be used when the equations of when the equation of a polynomial function is given in the transformed form. But not all equations will have this shape. Okay, so not all equations will mimic the exact shape of the parent polynomial function. So they will demonstrate actually some very cool patterns. So I'm going to write a note in here. This method is limiting. So this graphing method can be limiting due to the fact that it can help us graph only the functions that are written in the transform form. Sorry about this. Transform form. Okay, saying form twice, that sounds perfect. So, how can we graph polynomial functions otherwise? In order to understand how to graph the polynomial functions otherwise, what we need to understand is some of the properties or some of the features of polynomial functions. Now, the first concept that I want to go over with you is the concept of the family of polynomial functions. Now, a family of polynomial functions is a set of polynomial functions whose equations have the same degree and whose graphs have common characteristics. And probably just reading the definition is as confusing as looking at the many words in there. So nothing to worry. The equations and the examples explain things more easily. So here we have two equations. We have m of x, and we also have k of x. Now, notice that the factors for m of x are x minus 3, x minus 4, x plus 15, so 3 of them. And the factors of k of x are x minus 3, x minus 4, x plus 15. Oh, 3 of them, and not only that, but they are exact same thing. Okay, so here we have x minus 3, here we have x minus 3, here we have x minus 4, and then x minus 4. And here we have x plus 15, and this is x plus 15 as well. There is only one difference between these two equations, and that is the indicated by this coefficient. So here we have coefficient 2, here negative 15. Now, when this is the case, so when the functions have the exact same factors, they will have the same x-intercepts. And when the coefficients are different, we're going to say that these two functions will probably have a different stretch, probably different end behaviors, because this is negative, this is positive, but they will have the exact same x-intercepts. So that's when we say that these two functions make a family, because they have same roots. So it makes sense in a way. So what would they look like if we were to graph them? Now, I'm going to graph them in here. Remember, though, that this is not a precise graph. So I am going to sketch them, in other words. So it will have the intercepts at negative 15, or they will have the intercepts at negative 15, at positive 3 and positive 4. See, I am actually scaling them very generously. So the first one will extend from quadrant 3 to quadrant 1. That's because the behavior is that of a linear function with a positive slope. And the second one will have a negative coefficient, will extend from quadrant 2 to quadrant 4. Okay, so what they have in common, though, are the x-intercepts. The next thing that we want to talk about, which is very important again, is the order of a factor. So why do we need to learn the order of a factor? The order of the factor will help us determine the shape of the graph around the x-intercepts. The order of the factor is very easy to determine. It is the exponent to which each factor in an algebraic expression is raised. So for example, if we have f of x equals x plus 7 squared times x minus 6, then we're going to say that another way of writing it is x plus 7 times x plus 7 times x minus 6. So the equation of this function has 3 factors, and one of its factors, x plus 7, repeats twice. In this case, we say that x plus 7 is a second order factor. So, second order factor, whereas x minus 6 is a first order factor because the exponent of x minus 6 is 1. Okay, so exponent 2 makes it second order, exponent 1 makes it first order. Now, how does the order of the factor help us predict the shape of the graph? We're going to take a couple of examples which are pretty basic and are exercises that you are very familiar with since grade 10. I'm going to start with f of x equals x squared minus 4x minus 12. The factored form of it is y equals x minus 6 times x plus 2. So as you see here, this is a second degree function. It has two factors. Each factor is first order factor. Now I'm not going to pay attention to graphing the exact shape of the parabola. I'm going to focus only on the x-intercepts. So the roots of this equation, or the x-intercepts, will be at x equals 6 and at x equals negative 2. So here is negative 2 and here is positive 6. Now the vertex will be somewhere here in the middle, and the graph of the parabola will be, parabola opens up, okay, and it has two x-intercepts, one for each, produced by each factor. The next equation, which is g of x equals x squared minus 12x plus 36, can be written in the form, in a factored form, y equals x minus 6, x minus 6. So there are two factors in this equation, and both are the same. So in other words, we can say that's x minus 6 squared. So we're going to say that x minus 6 is a second order factor. Let's take a look at the shape of the graph at the x-intercepts. So 1, 2, 4, 6 here. So the graph will be a parabola, parabolic shape that opens up. And we're going to say that the x-intercept, which is right here, right, will be a turning point for the graph. So notice how a second order turning point, a first order just gets through the line or the axis. The last example, k of x equals x squared minus 2x plus 4. If we try to graph it by using the factored form of it, we won't be able to because we cannot factor x squared minus 2x plus 4. Out of curiosity, I'm just going to use Desmos, and graph this. X squared minus 2x plus 4, I already did that in there, will be the parabola. And as you see in here, the vertex of the parabola is above the x-axis, which tells us that the graph does not have any x-intercepts. So we're going to say that no factors, right, possible factors, or no roots, no x-intercepts. Okay? So in conclusion, we're going to say that the order of the roots always determines the shape of the graph at the x-intercepts. And to bring more light to it, a second order root will give a turning point. A first order root will give a straight line. If we were to have a third order root, then the shape of the graph would be similar to the shape of the third degree polynomial function y equals x to the power of 3. So for the roots of first order, we'll be seeing graphs that just get through the x-intercept. Second order, the graphs that make a turning point at the x-intercept. And roots of third order, the graphs will have an S shape at the x-intercept. And that's not too difficult to see or understand if we look at the equation of y equals x cubed this way. Y equals x cubed is x times x times x. So what we have in here is a cubic function of third degree. And we have seen the graph of this function before. And we know that the x-intercept will be at x equals 0 because these are the zeros of each of its factors. And that will be the case for any third order factor or third order root. The next thing we want to talk about is the end behavior of polynomial functions. The end behavior of a polynomial function will depend on two things. Number one, the end behavior will depend on whether the degree is even or odd. Even degree functions will behave like the basic parabola. Odd degree functions will behave like a first degree function or a linear function. The next thing we need to look at when it comes to end behaviors is the sign of the leading coefficient. Okay, that will change the direction of the y values, the trend in y values. So how does that work? In order to remember this, just think of the end behaviors of a linear and a quadratic function. And all even degree polynomials will behave like a parabola, so a second degree function. If the coefficient a is positive, and here we go, we are going to say that the function will extend from quadrant 2 to quadrant 1. So let me write it here. From quadrant 2 to quadrant 1. If the coefficient a is negative, the function will behave like a parabola that opens down, and the end behavior will go from quadrant 3 to quadrant 4. So from quadrant 3 to quadrant 4. All odd degree polynomials will behave like linear functions. So when a is positive, then the graph will extend from quadrant 3 to quadrant 1. And if a is negative, the function will behave like the parabola that, the linear or the line that goes down with a negative slope, and it will extend from quadrant 2 to quadrant 4. Okay? Do not try to memorize them. Think of or try to visualize and think of the connections between them logically. Now, the next very important thing we're going to talk about, they're all important things by the way, is the minimum and the maximum number of roots in an equation. So the number of roots or the number of the x-intercepts will depend on the degree of the function. The higher the degree, the more x-intercepts a function can have. And I will illustrate it with some examples, with quite a few examples actually. Now think of a second degree function, and I chose that as an example because it's something we're more familiar with. So a second degree function can have 2 roots, 1 root, no roots. So it can have 2, it can have 1 root, or it can have no roots. Okay, non-roots, let me say. So the minimum number of roots is nothing. The maximum number of roots is 2, which is same as the degree of the function. But in case you're wondering whether or not this is a coincidence, then I'm going to take an example of a fourth degree function. A fourth degree function can have 4 roots. Here we go, 1, 2, can come back again, 3, 4. But a fourth degree function can also have 3 roots. 1, 2, and the next root can be second order, so 3 of them. But it can also happen to have only 2 roots. For example, 1, 2, and then it doesn't touch the x-axis again. Another way or another possibility can be a function that goes like this, like a w, right? So here go only 2 roots. Well, it can also have only 1 root, and we've all seen the y equals x to the power 4 before. Okay? And it can also have no roots at all. And I'll make this example a bit more interesting. So you can have something like this. Just like it opens up, it can open down as well. So you can have 1 root or you can have no roots. So we're going to say the maximum number of roots is equal to the degree of the function. So as you see here, the maximum number of roots a function could have was 4. The minimum number of roots equals no roots at all. In odd degree polynomial functions, and as an example, I'm going to take a 5th degree polynomial function. We can have graphs of a 5th degree function with 5 roots. Here we go. 1, 2, 3, 4, 5. So going down. So that's 5 roots. So the maximum number of roots 5. But we can also have 1, 2, 3, and then 4 roots. So 1, 2, 3, 4 roots. Also, a 5th degree polynomial function can have 3 roots. So here we go. 1, 2, and then 3. So it doesn't make the connection with the x-axis in here. 1, 2, 3. And it can also decide to have only 2 roots. So 1, 2, 1 here, 2. And, sometimes it can also decide to have 1 root. Now, my question to you is to pause for a second, so pause the video and think, can an odd degree polynomial function have no roots, just like the even degree functions did? We're going to say most likely or for sure, no. And the reason why is because odd degree polynomial functions always extend across the quadrants. So it's not that you jump from quadrants that are above the x-axis, so from quadrant 2 to 1 or from quadrant 3 to 4. You have to go across to the quadrant across from where you start. So if you start in quadrant 3, you got to go quadrant 1. If you start in quadrant 2, you got to go to quadrant 4. So, and that actually makes it impossible for an odd degree function not to have any x-intercepts. So we're going to say that the maximum number of x-intercepts or roots will be equal to the degree, and the minimum number of x-intercept is 1. It must have 1 root. Okay. So in the next topic here, we are going to talk about the minimum and maximum number of turning points. And this is fun as well. Now, the number of turning points will depend on the degree of the function. And you'll see also it will depend on whether the degree is even or odd. The higher the degree, the more turning points a function can make, because the more x-intercepts it has to meet, right? So in even degree polynomial functions, and I'm going to take as an example a fourth degree polynomial. So we can have 1, 2, 3, 4, 3. Okay, so these are the arms actually. So we have one turning point here. Let me make this a little smaller. So 1, 2, 3 turning points. So fourth degree, 3 turning points. But a polynomial function of fourth degree can also have only one turning point. So, and the turning point would be right here. Now I want you to think for a second, can a polynomial function have 2 turning points of fourth degree? Another possibility can be this, as a matter of fact. So you can have a polynomial function with one turning point here. Okay. And it can make an S shape somewhere and then come back again. But I don't want you to think too hard for now. Okay. So we're going to say that the maximum number of turning points for an even degree polynomial, in our case fourth degree, is at most 1 less than its degree. And the minimum number of turning points, or at least it must have 1 turning point. An even degree polynomial, because it has to come back wherever it started. So if it starts at positive values of y, it must end in the positives. If it starts in the negative values of y, it must end in the negative. So it must make a turn somehow in order to get back to where it was, no matter where it travels. So we're going to say the least number of turning points will be 1. So in all degree polynomial functions, and I'm going to draw some fifth degree polynomial functions, so 1, 2, 3, 4, 5 here. So we have a turning point, 1 here, 2, 3, 4. So this will be the maximum number of turning points, which is 1 less than the degree. Another, and I'm going to borrow this example here. So 1, 2, 3, 4 as well. So another possibility for fifth degree polynomial function can be the graph is going here, 1 turning point, and then okay, so 1 turning point, like an S shape in here, so the function can have 1 turning point. Now, can a polynomial function have no turning points at all? So here is an example, the classic one. So this polynomial function has only this point here, and we're going to say that it's a fifth degree function and it doesn't have any turning points. The reason why is because odd degree polynomial functions do not have to turn back to the y values where they started. If they start in the negatives, they must end in the positives. If they start in the positives, they must end in the negatives. So they can manage not to turn back to the y values where they originated from. So we're going to say at least, we're going to say none, at most one less than its degree. So in general, for all polynomial functions, we're going to say that the number of turning points is one less than the degree of the function itself. But the least number of points for even degree polynomial functions is 1. They must have at least one turning point. The reason why is because even degree polynomial functions, if they start in the positives, they must end in the positives. So they must come back no matter where they travel. And even if they were in the negatives, for example, right, they must come back. Whereas in odd degree polynomial functions, the least number of points can be none. So they can decide not to come back and still maintain that high odd degree power. So I brought two examples in here to illustrate what we have learned so far, or to practice what we have learned so far. And in the first example, we have to sketch f of x equals negative x plus 2, x minus 1, x minus 3 squared. So first thing I want to do is identify the intercepts. So we have an x-intercept at negative 2, an x-intercept of 1, and an x-intercept at 3. So this is going to be first order, and this is a second order. So I know that at this x-intercept, I have to make a turning point. The next thing we want to look at is the degree of the function. So the degree of this function is made by the powers of each factor. So power 1, power 2. And what we do is we add all these powers. So the degree is 1 plus 1 plus 2. So that's degree 4. That's an even degree function. The next thing we want to look at is the leading coefficient. The leading coefficient is negative 1, so it's a negative number. So we're going to say that the graph will behave like a parabola that opens upside down. That opens down. Which means that the graph must extend from quadrant 3 to quadrant 4. And now I'm going to plot the intercepts. So we have the intercepts at negative 2, at positive 1, and at positive 3. Since we're starting from quadrant 3, it means that we are hitting negative 2 here. We need to go back to positive 1. That's a first order, so I can cross this. And I must make a turn to meet with the next x-intercept at 3. But because this is an order 2, I must make a turn right at the x-intercept, because that's an order 2 root. That's first order, and that's a first order. But x equals 3 is a third order, a second order. Gosh. So the next example is for you to practice. I will go over it, but you can pause the video and try it on your own. So again, the x-intercepts are at x equals 2. That's a third order. And x equals negative 3. That's a first order. So x equals 2 and negative 3. The degree of this function is 3 plus 1, which makes it a fourth degree function. So that's even. And the leading coefficient is positive because it's positive 1. Now, since this is an even degree function that has positive coefficient a, means that the function will go from quadrant 2 to quadrant 1, just like the parabola that opens up. Now, x equals negative 3 is a third order root, so we can start the graph from quadrant 2 and hit negative 3 and cross the axis there. Now we must go back to our next x-intercept, which is at 2. Now remember that this is a third order intercept, which makes the shape of the graph in an S shape. So as we approach it, we are going to go ahead and make this shape as pronounced as we can. Okay, and that would be the graph for degree function, even degree function, right, with a first and a third order root. So you have a couple more, another example very much like the one we just completed, so you can do this on your own. And in the next example, which is a little bit different than the previous examples, we have to use reasoning to determine the equation of the function given this information. So it's a cubic function with zeros of -2, 3, and 2/5. So whenever I'm given the zeros of a function, I write them this way: x equals -2, x equals 3, and x equals 2/5. The next thing I want to do is predict the factors based on the roots. So x equals -2 must have come from the factor x plus 2, making x plus 2 equal to 0. X equals 3 must have come from making x minus 3 equal to 0. X equals 2/5 must have come from x minus 2/5 equal to 0. So the factor for x plus 2 equals 0 must have been x plus 2, x minus 3, and I'm going to do a little trick to this one here. X minus 2/5 will actually be 5x minus 2, because we don't like to use rational coefficients in a polynomial function, and very often you will be asked to write the equation with integral coefficients, which means that the coefficients of each term must be, or the coefficient of each term must be an integer and not rational, not a fraction. So these are all three factors, and I would say that the cubic function must have the factors x plus 2, x minus 3, and then 5x minus 2. And I'm going to throw in a coefficient a here to indicate that that can happen as well. So this is a possible equation of the function with the given information. Now, in the next example, I would like you to go over the shape of the graph and determine the roots. Please try to ignore actually this part in here, which is, I don't know why I cannot get rid of it for some reason on my computer. Okay, and based on the roots that you see in here, you can predict the equation of the function. And this is how I do the first one. So I see that this function will have a 0 at 1, 2, 3, 4, 5, 6, -6. So x plus 6 must have been one of the factors. A 0 at -12. So 2x plus 1 is the next factor. And a 0 at 3.5, which is 7/2, which is 2x minus 7. So this would be the equation. We still don't know what the value of a is, but we do see that it has an intercept, a y-intercept at -1. So we're going to use this to find the coefficient a. So if x equals 0 and y equals -1, that means -1 equals a, 0 plus 6, 0 plus 1, 0 minus 7. So a times -42. Or let me just show the work just in case here, but I'm pretty sure you're fine with that. So -42a, that will give a equal to 1 over 42. So to make the equation complete, then we'll write in here 1 over 42. Now the range of this function is any real number y. And for the n behaviors, we're going to say that as x approaches negative infinity, y approaches negative infinity. X approaches positive infinity, y approaches positive infinity as well. Now, in the next example, you have to note that these are the roots or the x-intercepts. At x equals negative 7, we have a double root, and at x equals 6, we have a single root. So the equation will be y equals x plus 7, second degree or second order root, and x minus 6. We do not know what the coefficient a is, but we can use this point on the graph to help us find it. 1, 2, 3, 4, 5, 6. So we have a point with x equals 0, y equals 6. So which means 6 equals a 0 plus 7 squared times 0 minus 6. 6 equals a times 49 times negative 6. These two will simplify to negative 49a. So a equals negative 1 over 49. So the equation is negative 1 over 49. So for the range of this function, we're going to say y is any real number. And behavior, x approaches negative infinity, y goes to infinity. X approaches positive infinity, y goes towards negative infinity. In the next equation, we have an x-intercept at x equals 0. That's third order. And an x-intercept at 4. That's a first order. So the equation will be sum a, x to the power of 3, x minus 4. We can use the 0, 0, the x-intercept in there, to figure out what the value of a is. However, we have to watch out and not to use the y-intercept that is in the meantime the x-intercept, because that won't help us find the coefficient a. But we can actually use any other point on the graph. So it seems here that at x equals 2, y equals 3. So 3 equals a, 2 to the power of 3 times negative 4. So 3 equals 8 times negative 4, which is negative 32. And that will make the value of a negative 3 over 32. So the equation is negative 3 over 32 here. As x approaches negative infinity, y is approaching negative infinity. As x approaches positive infinity, y goes towards negative infinity. The range of this function here, 1, 2, 3 and a half, is y any real number, but y has to be less than or equal to 3.5. Remember that in odd degree functions, like the first two examples here, there are no limitations in the range, but in even degree functions we always have a highest point or a lowest point, which limits the range. Well, this was quite a long lesson, and I thank you very much for following and listening, and I hope this lesson helped you understand polynomial